for today, so I'm going to go really fast. If you start feeling it's too much, like you can just surrender, put your arms up, and I'll zoom ahead to something else. All right. So I'm going to start by showing slides that were presented by Professor Hai Wang, currently of Stanford University, at the Combustion Symposium in 2010. So it's a long time ago, right? 14 years ago. But he focused on a very important problem that as far as I understand, is not yet solved. So I thought you guys should understand what that is. So this is all about how soot is formed. As we talked about last time, particulates are a very serious contributor to human mortality and maybe the most deadly thing that's caused by combustion. And so it's pretty important to understand it. In some respects, we understand it because there's empirical models and methods to kind of control particulates. But at a more fundamental level, we don't really understand it. So that's what this slide shows about. So you think, well, why, if you have a high temperature gas phase system, why would you ever make solid stuff? You definitely do. This is how we actually manufacture carbon black, how we manufacture fumed silica and titania, a lot of other stuff. So it definitely does make solid stuff. Gas suddenly, spontaneously, at high temperature, forms solids. But it's kind of weird because you're losing a lot of entropy if you make a gas into a solid. So it seems like non-intuitive that that would happen. And also, why would it happen at high temperature? You think it might happen at low temperature because there's where the enthalpy effect would be most effective and the entropy would be least important. But in fact, we often see it happening at high temperature. And there's kind of two different types. There's type 1 are enthalpy driven. So if you make a metal oxide, for example, titanium really wants to react with oxygen. It's a very negative delta H of reaction. And so you can get that to happen kind of regardless of the entropy because the enthalpy is really driving it so hard. But soot is not like that because the reaction, say from a hydrocarbon to carbon plus hydrogen, has a positive delta H, so it's endothermic, and yet it still happens. And the delta S is greater than 0. You may say, why is that? I'm making a solid from a gas, but the key is you're releasing many moles of gas, of hydrogen, and that has a lot of entropy, and that's what's driving the process. Let's see if we can make this work. So the driving force is, you have to have the delta G going down. And if you look at it very carefully, you can see the delta G is going down, but not very much. But eventually, as it gets towards the very far right there, the lower right, you see if you make graphite plus all the hydrogen, that's definitely downhill. But all the intermediate hydrocarbons are maybe slightly downhill from the starting hydrocarbons, but not that much. And this causes a lot of trouble for the modelers because if you get very small errors in the computed free energies of these things, you might get them out of order, which one is uphill, which one's downhill. And if you ever compute it to be uphill, the model will never make that product as a major product. It has to be downhill. You have to, because as you're going towards equilibrium, you're always trying to make delta G go down. So getting the numbers right is really crucial and kind of tricky. But you make it anyway. I mean, empirically, this has been known forever. The cavemen used it to make the paintings that they put on the caves. You've seen it every day, every time you have a fire. People used to use soot to make tattoos. So this is like a very well-known thing. You can do microscopic examinations, like electron microscopy of the soot particles, and you can see that inside what's looks like a round soot particle are actually these little like flat layers, maybe like an onion. If you look down really closely, you can see that they're at the scale of like benzene rings. And soot changes a lot. So you start to see some solid forming, say by light scattering, you can see it. If you stop the reaction at that point, the soot has a lot of hydrogen in it, But if you let it cook at high temperature longer, more of the hydrogen leaves, and you make more carbonaceous compound. So mature soot has a carbon to H ratio about 8 to 1, so it's pretty much carbon with just a little bit of H's on it. But when we started, our fuel had more hydrogens than carbon. So through the process, we keep losing hydrogen atoms. And to get all those material with all carbon and hardly any hydrogen, there's kind of two options. You can make stuff that's like diamonds, where each carbon is bonded to 4 other carbons. It's a tetrahedral carbon. And you can do that, actually, and that's how people make artificial diamonds. So if you ever buy a cheap diamond, it was probably made that way. But if you just let it happen naturally in a flame, more commonly you make kind of a material where each carbon has 3 carbons bound to it, and a more or less flat or slightly curved planar configuration, sort of like graphite or graphene. And that's mostly what you see inside soot. And then the soot, the middle picture is really important. If you look in the far right, you're seeing the blow up of what it looks like. But if you look at it in the middle one, you can see what happens. You get these little balls of soot that are on the scale of maybe 10 nanometers, and they stick together. And they kind of form a continuous agglomerate, but it's kind of has a lot of porosity. Do you see how it's there? You have like this train of little soot particles, very tiny, and they're all kind of mushed together into this big agglomerate thing that's pretty porous. And exactly how porous it is really important for its properties, like light scattering and absorption, what its surface area to volume is. And all those properties matter a lot. And so soot particles not only are bad for human health, but they're actually good for other things. We use them as the inks in our printers and Xerox machines, or these little black powders. But to work in inks, they have to be, actually in your pens, but to work as inks, they have to have exactly the right kind of structure and the right kind of porosity so that they'll suspend well in the liquid of the ink. And that way you can make them make a nice writing and write your signature very well. So there's companies like Cabot that sell like thousands of grades of soot for different purposes. Certain ones are good for putting into tires to make the tires stiffer and stronger. Other ones are good for Xerox machines to get charge on them and use like a charge effect to make the reproductions to print. Other ones are used for inks in your pen. Another one, a different kind of ink that's in your inkjet printer. All these different things. And you can make them all. And of course, but all of them pretty much, if you breathe them, are not recommended. So soot is really versatile, and it's used for a lot of different things. And even the carbon it has a conductivity, and so it can be a good way to conduct electrons. And so some solar cells are based on using different types of carbons as the conductor as well in those. But it's really bad in the air, and we make a lot of it. So our airplanes spew out quite a lot of particulates. The particulates eventually drift down to Earth. If there's still free particulates when they come down to Earth and there's some poor person there to breathe it, then it can be very bad for the health of that person. A lot of them will end up instead getting absorbed into water droplets or nucleating water droplets. And that's one of the reasons why you get contrails behind airplanes or behind ships, because the particulates go up, and if the air is supersaturated with water vapor, the solid soot surface nucleates the formation of the drop, and then that will basically lead to a whole bunch. If you have a lot of particulates, you'll lead to a lot of droplets, and that will make a cloud, and that's the contrails that you see. And you guys have all seen all of this before. And some of these, like for example, in the US now, this bottom middle picture would be like illegal because the truck would have to have a diesel particulate filter, which would capture most of the soot. But the older trucks, or if somebody takes their filter off, this is what's going to happen, or if the filter gets a hole in it. And in the old days, really old days, the 19th century, people used coal a lot to power trains. and you make a lot of soot from coal. We use coal a lot now to make electricity, and again, if you just burn coal and make electricity with no emission controls, you'll make a lot of soot. But if you do in a modern power plant like in the US, you have this very complicated process that tries to capture as many particulates as it can. And so the total particulates emitted is a very small number if you have the good emission control system. And the emission control system might be as big as the whole power plant. You have like all kinds of filters and electrostatic precipitators and all kinds of stuff to try to capture all the particles. Some places they still burn coal without emission controls. I did a study of China. In China, at the power plants, they have very good emission controls. So it's just like US, basically it's good. But they have some older burners that they don't have regulations on. And particularly at the oil refineries, they get emissions, a lot of emissions from the coal that's used to boil, to power the distillations. Because they use coal as the fuel, because in China, natural gas is expensive. In the US, you would use natural gas at the refineries to power the furnaces. But in China, they use coal, but some of those oil refineries were built before they had any regulations, and so they have a lot of emissions. So right near the refineries, you have a lot of pollution, and it's not really from the oil, it's from the coal that's used, that's burned. And if you look around the world, there's many oddball things like this. Actually, New York City has some old apartment buildings that the heating for the building is done by coal with no emission controls. And so that was actually a pretty significant fraction of all the particulates in New York is from just a few buildings. I think there's like 40 old apartment buildings got grandfathered in when they made the regulation, and they're still polluting like crazy. When cruise ships or big ships come into harbors, if their engines aren't working perfectly and they use lousy fuel, they might be emitting quite a lot of particulates. And so sometimes if you go near a port where a cruise ship has come, you'll feel it's hard to breathe because the ship is emitting so many particulates. When it's out in the middle of the ocean, probably doesn't matter. The ship is moving and leaves its particulates behind, they fall in the ocean. But if you go into a port, usually a lot of people live near the port, and they're all getting polluted by the particulates. And then, sorry, question? No. Then the soot affects the climate in a whole bunch of ways, and it's super complicated. And I really don't understand this, so I'm not going to explain it. But basically, it affects the cloud formation. It affects some of the soot deposits on the Earth and makes the surface of the Earth darker, so it absorbs more heat. Sometimes it lands on top of snow. It makes it darker and also helps to melt the snow near where the black stuff is. So you get all kinds of different effects. Some of them heat the Earth, some of them cool the Earth. On balance, it heats the Earth. And it's quite complicated to figure this out, and I don't know about it. But there's people who specialize just on climate modeling, and they're pretty convinced that it's a significant contributor to the warming of the Earth. Not as much as CO2, but still pretty significant. All right, so there was back in 1965, people said, wow, we really need to understand how soot is formed. And so I'm here to tell you today, it's almost 60 years later, we still don't know. So maybe one of you in this room will be the one to figure it out. We had a lot of smart people work on it, Frank Locke and Bockhorn and many different people have worked on this. And a very important modern thing is to try to figure out, can we make the combustor be more efficient at burning out the soot? So as I mentioned before, most of the combustors we use are partially premixed. So we have a premixed rich flame. Following that is a zone that might make soot. Following that is the diffusion flame that would burn most of the soot out. But empirically, it doesn't burn all the soot out. So some soot gets through somehow. And can you somehow make the design of the combustor to try to reduce the amount of soot you made in the first place, or make it more efficient at burning out the soot afterwards? And that's a really important thing. And a lot of people have worked on this. So like the top right picture is an idea where you would first try to make a stable, rich combustion, and then have a a zone after that where you try to have it lean, still high enough temperature that it'll burn the soot on the way out. And people make like aircraft engines and gas turbines and stuff trying to accomplish this. One complication is that we don't really have a good chemistry understanding of how the soot is formed. So the chemistry models that go into the simulations of those different combustor designs are not perfect. And so this is an issue. In general, we know that once you get the first aromatic ring, you pretty quickly get the second aromatic ring and the third aromatic ring and the fourth aromatic ring. And then, as best we can measure, all of a sudden you see really big stuff with lots and lots of carbon. And exactly what happens between the fourth aromatic ring and all this carbon is like really unclear. And then you can look in detail, trap the nascent soot at different heights above the burner, and do all kinds of analyses to try to figure out about it, what's happening. And a lot of people have done that. So people like Bockhorn, for example, Sarafim, Hai Wang, have all worked on this thing. Diana. And we have different names for the different parts. So the first part in the lower left is the gas phase chemistry, and that's mostly what I've talked about in this course, where you know all the molecules and you work out all the rate constants. Then the next one's the PAH chemistry. So I would say today we're going from the gas phase chemistry up towards the PAH chemistry and into the early PAH chemistry. But the number of possible reactions and species and exactly what the thermo is and exactly what the rate constant is not so clear when you get to the bigger PAHs. And then somehow like a miracle occurs and you have nucleation, and then all of a sudden you see all the soot. Empirically you see all the soot. Exactly how the nucleation worked is not so clear. I would comment that this is true for many phenomena where you have nucleation. Nucleation is really hard to catch because typically you see nucleation where the system really wants to grow to be a big giant solid. And almost the instant you have nucleation, immediately it grows. So what you can measure experimentally is big stuff. You don't see the little nuclei. The nuclei very rapidly grow up. And the nuclei are hard to form. There's typically like a free energy barrier to form the nuclei, and so you don't have hardly any nuclei. So you see the precursors, lots of them, and then you see a lot of the final stuff, and you don't see much in the middle because the steady state concentration of the nuclei is really tiny and hard to see. But they're big enough that they're hard to handle with molecular dynamics and quantum mechanics. And so you get things you need to have, 100 or 1,000 carbon atoms. Who knows? We don't know what size the nuclei are. And then we have to figure out how to compute how they would possibly come together in a way that would form a nucleus. And mostly we don't know. And it's true for all kinds of crystals. I work on making drugs. You want to crystallize a drug, we don't know. If you want to make titania, we don't know. If you want to make fumed silica, yeah, we don't know that one either. Basically, we don't know much about nucleation. This was the status in 2010, or around 2010 when Hai Wang gave this talk, is you can do kinetic Monte Carlo simulations and understand why you get the shapes of the soot that you see. And this work here is shown by Franklock. There's also really good work from Marcus Kraft, where you can do quite detailed simulations. And sort of once you have a nucleus and it starts growing, you can model very well what the shape would be, why you get the different kinds of agglomerates, if you change things, how that's going to change. And this is super useful for companies like Cabot who are trying to make soot of particular morphologies, that they really have very good understanding of this. So once you have the nuclei, people can predict very well what happens to it. And the real challenge is to figure out what the nuclei are and why you would make nuclei. You can measure the particle size distributions. So this is from Marcus Kraft in the lower left. And you can see the distributions. You typically get this two-humped distribution where you have a bunch of low molecular weight stuff, and then you form some higher molecular weight stuff. And that higher molecular weight stuff is the stuff we're going to call soot, or the particles. And the lower molecular weight stuff is like the chemicals that are forming the particles. And there's typically like this gap in the middle. You can see experimentally that the stuff at the middle size I'm sorry, I don't have an arrow here. Can you see this? That little spot there? There's like a minimum in the particle populations that corresponds to a certain size. And that's somewhere in there we think is maybe the nuclei. And then this grows after that. You get more material that's heavier and more material that's lighter, but you don't have much of that particular size. People have done really great job with the analytical chemistry. So you can take a soot particle and figure out exactly what's in it with all kinds of measurements of how the carbon atoms are bonded, what the impurities are, what the molecular weight distribution is. In the soot particle, you typically have not just the solid framework, but you have other hydrocarbon stuff stuck in the pores, and you can measure that too. You can measure exactly how many hydrogen atoms you have per carbon, all this kind of stuff. So there's really excellent work. This is like pretty messy. So this is the mass spectrum. I mean, look, this is all the way up to 1,800 atomic mass units. And there's like a peak at like every mass unit. Every mass, all the way up to 1,800, there's some amount. But they're not all the same. And you can go through and figure out like certain masses are most favorable. And you can help to understand, you can understand something about what's going on from that. And you can vary things like the phi or the distance above the burner, and you can see how this particle, you start to see soot like at a certain height, and then you can see as the things go on, the soot gets larger and larger particles, a broader distribution. And this later part is pretty well understood of what's happening. All right, so the key questions are like what's going on to make the polycyclic aromatics that we think are somehow the nuclei of the soot, and exactly how do we get from molecules, which are really tiny, to particles, which are much bigger, and exactly the evolution of the soot, because people know it changes, but exactly how much it changes and why is also not so clear. So for example, when you first make soot, it's red, and then later it turns black. I don't know why. So presumably the chemical structures have changed inside. The black one is very well studied. We have a lot of black soot. The red one is kind of weird, and you don't make much of it. But you can see a little absorption at red right before you see it turn all black. And there's a mechanism called the Hacke mechanism that was proposed a long time ago about how soot can form from acetylene. Is it really the right mechanism? Is there something else going on? Right? It's pretty hotly debated in the chemistry journals about exactly what the real key mechanisms are to form the soot and how it grows. But the Hacke mechanism is definitely at least partially right. So this is the Hacke mechanism. You start from acetylene, and you add an AH here, and then you make a radical, and then the radical adds to another acetylene, and you lose an AH to make another radical and add another acetylene, and then it can curl up and make benzene. And then this can go on, you can do the same kind of thing and add more to the benzene and make phenylacetylene, and then eventually a 2-ring thing, and so on and so on. You can make 3-ring thing and so on. There was a whole group of people that study this, most famously Frank Locke, but a lot of other people too, to figure out all the steps. Jack Howard at MIT proposed a slightly different mechanism. Both of the mechanisms happen. They all depend on the reaction conditions. A little complicated, but this is all kind of now understood pretty well. And you can do kinetic modeling of it and all the sensitivity analysis for the first couple ring formations. And the key conclusion is that the chemistry is like super complicated, and there's a lot of reactions. See, all these reactions have high sensitivities, all the ones you see with bars. That's a lot of reactions to be sensitive to. And that's like a headache for the modelers because it's like not clear what's really the rate determining step. And I need to spend a lot of time to make sure I get good numbers for all of those rate coefficients. And each one of them is like a whole project to measure it. But people have worked on it pretty hard. So, and this was a long time ago, it's 1997. So since that time, many of these are now understood better. Whereas by comparison, if you compare it to flame speed is very simple by comparison. There's only a few reactions that are really, really sensitive. And so once you get those numbers right, your models, you get pretty good flame speeds. But soot is not like that. It's really complicated. Thermo is a really great way to look at it, and you can try to list all the different intermediates you think would be there, and just which ones would be thermodynamically stable compared to others. And a key insight is that many of the reactions are partially equilibrated in this soot because the barriers aren't that high at the high temperature you're at, and the thermo is not that different, so almost everything's pretty reversible. And so you can learn a lot by just worrying about the thermo and trying to list out all the species and try to figure out what's the thermo. And you can see the whole range here is only 1.5 kcals per mole between all these different species. So you can see the problem for the modeler is you need to have very good accuracy if your total range of the chemical species is only 1.5 kcals in enthalpy. Then that's really not so great, right, for trying to model. Later, after Haka, people discovered the propargyl post-propargyl recombination. This is Fahrenstein discovered in 1990, and NIST they measured, and they found if you get two of these C3H3 radicals together, very rapidly you see benzene and phenyl radical plus H. And Miller and Klippenstein modeled this very carefully, and we understand this one pretty well now. Then later, a whole bunch of other mechanisms were proposed. Here's some of them. Actually, even after this talk, a whole bunch more of them were proposed. So you can almost, once a year, open up Science or Nature, and somebody else has proposed another mechanism of how soot is formed. And they all have some basis about why they think that mechanism and why it got published. But I think it's really mostly not that clear which ones are really the most important in different conditions. And fundamentally, the problem is we don't really understand the nucleation, which is super key. So even if we understand all these small molecule chemistry correctly, we're missing like the key step. We don't know what the key step really is. This pursuing trying to understand soot has been really great for development of experimental techniques. And several groups have made some really nice experimental techniques. So this is from Fei Chi's group using synchrotron methods. Later, Nils Hansen in his group, the Advanced Light Source in Berkeley, made a whole bunch more very fancy apparatus, measured all kinds of stuff about the soot, nascent soot, and different parts of the flame, and all the different molecules are forming. Really great experimental work. So we actually have quite piles of data at particular conditions. Earlier, there were some German groups that did some really nice experiments too. There's quite a lot of really great experimental data. They're all for particular flames measured a certain way. So we don't have a general picture, but for a lot of those flames, we have a lot of data with great detail about all the different structures. You see all these different masses all measured very carefully. Sorry, I did this already, did I? Go in the wrong direction. All right, so summarize the polycyclic aromatic hydrocarbons, that's the multi-ring species. The formation is sensitive to the flame chemistry, the local conditions, the fuel, and the fuel composition. You change any of those things, you'll change this chemistry, and you can measure the changes. Not so clear in the real systems, like in the jet engine, which is actually the most important thing. All you see is you put stuff in the jet engine, you get soot coming out the back at the tailpipe, but exactly what happened from here to there, not always that clear. Some of the steps are really understood. I would say in general, the sigma radicals, where you pull an H off of benzene and the radical is sticking out parallel to the plane, that's kind of chemistry really well understood. But there's another kind of radical where the radical's orbital is perpendicular to the aromatic plane, and those radicals much more poorly understood. And I think not 100% sure how important they are. My own group tried to work on this using RMG, and in 2019, we were able to get up to the third 3-ring aromatic. This is acetylnaphthalene, so it's 2 6-membered rings and a 5-membered ring. And that one, we're still getting pretty good. But around here, this is where RMG started pooping out, that we didn't really have enough capacity to model all of the reactions very well. And the experimental data shown here in the gray bands are measured by Patrick Oswald and his group at DLR in Germany. The red lines are the predictions of the RMG. And this is, again, similar to what I showed before, is that you can see the RMG is sort of correct at predicting what's happening. But if you look in detail, it's like not exactly correct. And then trying to figure out why it's not exactly correct is really complicated because the chemistry is super complicated. These are already something like 3,000 species in the models. This is a flow reactor, yeah. They start with a flame. They mix up methane and oxygen. It burns it, but they have way excess methane. And then, so most of the pipe is pyrolyzing the methane and is gradually growing up to make all these aromatic stuff. And they ran a lot of different conditions and different temperatures. And they had very good mass spectrometry to measure what they had. And that's how this was worked out. And they had to calibrate. So many kudos to the experimentalists to get it. So they measured like 100 species with calibrations at bazillions of different conditions, getting all these points. And you can see is these gray things are like a cloud of data. Each of these is a separate experiment. So these guys really worked. Congratulations to hardworking Germans. All we had to do was run the computer. Bing. So we had a much easier time than they did. So how the nucleation works is not clear. There's a bunch of different proposals by different people about even what the stoichiometry is of like how many hydrogens have you knocked off before it nucleates, and then exactly how it works. And these are all like hypotheses, I would say, without proof. So these are proposals, have not really been that well tested. Actually, some of them I think have been proven wrong, but none of them is really convincing that it's really the right explanation. If you think that you must have a second order process somewhere in there because you see the bimodal distribution of this size distribution, and you can only get that if you have a second order process somewhere. But exactly what the two things are that are reacting to each other to make it second order is unknown. Yes, you can see the data is very well known. So the experiments have been done great by many groups, and they all agree. And so you get these same kind of size distributions all the time, all different kinds of flames. And you can do the mass spec, and you can see periodicity, which is interpreted as you're starting to make layers, and they're sitting on top of each other, and you get like certain size chunks stick together somehow. The conclusion from that, these guys concluded by this, that this says that this is not true, but I'm not sure I believe it. But anyway, it's just, hard to tell what exactly is happening. The process is very complicated. Yeah. I'll just step up here. Let's see if we can say anything. So you can do analyses of some of the hypotheses, and the main hypothesis is two things stick together. And for a long time, people thought, oh, just van der Waals. You have two big giant clumps of carbon atoms. They'll just adhere to each other by van der Waals attraction, which is true, they do. But then if you do the calculation carefully, you realize at these high temperatures, the entropy of separation is bigger than the energy of the van der Waals attraction. So they should not stick together. So there's a bunch of literature that's all about the van der Waals thing, but it can't be right if you do the numbers. So it has to be something else that's making them stick together. And so basically, yeah, all these hypotheses, at least according to Hai Wang's analysis, none of them can be true. So we're left with no explanation of how we make this up. Some people say, well, maybe spontaneously some of the big carbon things start forming radical sites. And there are some examples. So if you have a polyacetylene, when they get long enough, they actually just spontaneously form diradicals. And that's known by spectroscopy. So I think it's not known if you do this with aromatic rings, does it spontaneously form it? However, it is known that if you get a pile of coal, a piece of coal, and you take it, put it in electron spin resonance, it has radicals in it, even at room temperature. So coal, somehow there's a way that you can just make room temperature radicals that are stable at room temperature if you have a big enough chunk of carbon. Exactly how that happens, nobody knows. But it's definitely true and measured by many people that just you take any piece of coal, it always has radicals in it. So that makes people think, well, maybe all these nascent soot particles just have radicals in them somehow. Yeah. I think only coal, but that's a very good question. And maybe probably people know now for graphene, which I do not know, but that's a great question. Do all types of carbon clumps do this, or is it only coal somehow special? I don't know. That's a very great question. A very interesting thing about graphene sheets like this is that the zigzag edges have very unusual electronic structure. And actually, I'd say graphenes in general have very unusual electronic structure. And there's like a whole ton of papers about if the graphene twists a certain way or has a certain defect. All these different things cause really different weird electronic structure stuff. And one part of it is that the zigzag edges look like they're open shell singlets. That means that they're free radicals, basically. There's free radicals, but they're paired, but they're separated, like the one that spin up and spin down. And then principle, they could each react separately. And in fact, coal, because it has the radicals, if you put it in presence of oxygen, you can just make peroxides directly from the radicals. So that's kind of interesting. So we have all these ideas about what might cause soot nucleation, but there's some evidence that basically argues against all of them. And then we have a bunch of oddball observations that we don't know what to do with. This is the short summary. You can definitely go ahead and do the simple mechanisms that we're sure are right, for example, the Hawking mechanism, and you can derive the mass growth rate, and you'll see that it's proportional to how much radicals you have, which makes perfect sense. We always have, most of combustion chemistry and pyrolysis chemistry, everything scales with the concentration of radicals. So that's not surprising. So the whole key then is how do you make the radicals? In the particular conditions you have when you have soot nucleation happening, are you supplying enough radicals to keep on driving the process forward or not? And people have tried all kinds of stuff. So neutron scattering, densitometry, photoionization, many things to try to figure out what's going on. And they get more and more data to observe what's going on, but it doesn't come with explanations. It just comes with more data. So we have lots and lots of interesting observations about what happens when soot starts to form, but none of them just says clearly that this is the explanation of what's really happening. Or we know what happened, we just don't know why it happened. So one possibility is that maybe somehow we are making some kind of structure that just wants to be a radical all the time, and then the radicals live. And that way, no matter what's going on with radical formation, it doesn't matter because you have radicals that are just intrinsically there. And then that would make things bind more strongly because if, say, two radicals get together, it makes a chemical bond. And that's a much stronger than a van der Waals interaction. So that's like a possible explanation. But we haven't figured out exactly which radicals they are, and the thermo, not known, many things not known. You can see a lot of weird stuff when if you have the nascent subparticles hit onto a surface and then do electron microscopy on the surface. Well, you can see it looks like kind of like a soft-boiled egg or a fried egg. You have like a yolk and the white around it, and you get this shape. And so what does that mean? So one interpretation is maybe this yolk part is where the soot is like really solid, and maybe this soot has some liquids in it that kind of oozed out when it hit the surface. That's a possible interpretation of this. And so Hai Wang did IR spectroscopy trying to see what he could see that would be liquid, and actually he did see quite a lot of hydrocarbons with a lot of hydrogen on them, kind of mixed up with this other carbonaceous stuff with very little hydrogen on it. So somehow it's like maybe the soot is acting like activated charcoal and absorbing stuff into the pores. It's very sensible, probably that's true. It makes it confusing for the analytical chemistry because if you measure like the total amount of hydrogen atoms in this ball, you're measuring both the solid ones and the liquid ones, where really maybe you like to separate them. But how to do it, capture these nanometer particles and directly extract the stuff out and measure everything separately is kind of tricky to do. But as I said, the coal has radicals in it, known since 1960s. The soot volume fraction you get doesn't make any sense, but if the soot always had radicals, maybe that would work. The soot, when you pyrolyze these particular compounds, makes a bunch of radicals, measured in 2005 by Serafim's group, Eddings. And a particularly bizarre thing is that soot absorbs water even though you'd think it to be hydrophobic. And what does that, why? That's also not known. All right, so that's apparently the soot can continue to grow even if there's not a lot of H atoms driving the process, suggesting that maybe there's some other source of radicals, which possibly is just the soot itself is making radicals somehow. But exactly what that is, not clear. All right, I think maybe that's enough for this. So we have different pictures. This is a picture from the 1980s and 1990s about what they thought was happening, where you're making a bunch of aromatics, and then they do van der Waals binding to make planar things, and then they glom up together to make balls. That's now known not to be true because the van der Waals complexes would not be stable, so you can't have these intermediates. So now the idea is that maybe you make some really big ones, and we just don't happen to measure them, and these guys are big enough that they can stick together somehow, or maybe they have some radicals with them, and somehow the radicals make them stick together. But on top of it, you have a whole bunch of hydrocarbons sticking into all the pores, making it slightly confusing about what's really happening. And so we always think about, like, it's so hard in our models to make soot. We never have enough reactions to make soot. If we want to make a model make soot, we typically have to put an artificial reaction that just is a fast reaction that artificially jumps from chemicals to soot, and we make it irreversible. Because if we ever try to put in the thermo, we never get it right, and it always wants to go back. But you know, when you from nature, it's super easy to make soot. In fact, it's hard to not make soot. We have to do very special combustor designs to avoid it. Basically, it wants to happen all the time. So really, from nature's point of view, it's all downhill. That it wants to go to soot, and it's just odd that it just doesn't immediately form soot. So that's shows that the modeler's point of view might not actually match up with what's really important. So summary, you know, as we know, the fuels are a big positive thing for society and a big problem for society, and we have to change them. One of the several problems is the particulate formation. We don't really know it. And I just talked about soot today, but actually there's a very similar problem at room temperature. In smog, it just spontaneously forms particles. And exactly how that happens, also not known. And also super important. In many cities, about half of the mass of particles is from soot directly, and the other half is from this secondary organic aerosol formed by the smog. We need to understand that one too. We have quite good understanding of the small molecule combustion chemistry and some of the fuel pyrolysis. And we're starting to get quantitative understanding of the first couple rings, of how we can form the first couple rings where it matches the experiment really well, like the example I showed from Chu's model for Oswald's experiment. And there's several other cases like that recently. But what's happening when you get to past 4-ring aromatics, I think, is still pretty mysterious. Somehow something's happening dramatic where the system is suddenly jumping from itty-bitty tiny molecules to big, gigantic stuff very quickly, and we don't really know why. And just trying to go ahead with the RMG approach, or we try to list every single reaction and follow what happens, you can get somewhere, but man, it really exponentially expands how complicated the chemistry is, and the computer gets more and more trouble. So getting from, you know, zero rings to 1 ring, no problem. People were doing that like at 2000. Going from 1 ring to 2 rings, that was took 10, 15 years. Going from 2 rings to 3 rings, another 5, 6 years. We're still in the middle of doing 3-ring things right now. Experimentally, for sure it goes up to 4 rings in great quantity because we measure that. So we should be able to do that, but the chemistry is so complicated trying to get it all straight. what happens magically after 4 rings, we really don't know. All right, so that's soot. Any questions about soot? All right. So then I will start ignition. All right. All right. So there's 2 kinds of ignition that we commonly experience. The one kind that you've probably done if you ever celebrated a birthday with your friends is you light a candle, right? So you light a match, use the fire from the match to light the candle. It's like an induced ignition where the spark from making the match, or in a car engine we have a spark plug. We intentionally blast the system really hard to go to high temperature, and that forces the ignition to happen. And so that's a really common way. But then another way you can ignite is auto-ignition, which is spontaneous combustion. If you just have a fuel-air mixture and you let it get hot enough and stay together long enough, it'll just burst into flames. This can be a hazard. You guys probably are familiar that sometimes this happens because of house fires, where people have like some kinds of oils that people use to paint with are very susceptible to oxidation. And if they're not stored properly, they can just spontaneously ignite even at room temperature. The kinds of fuels that we use in engines don't ignite at room temperature like that, but they will ignite at the temperature you get inside a piston when you compress them. And in fact, that's how diesel engines work, is we ignite them by compressing them. In this section, I'm just going to talk about the auto-ignition one. This other one, induced ignition, it's super important too, and people spend a lot of time on sparks and how to use different kinds of igniters. Professor Ju is an expert on how if you add the plasma, you can really force the things to ignite, even if they don't want to ignite. But I'm going to talk about this other one where it's just spontaneous ignition. And it's because diesels rely on this. And diesels are really important engines we use. And we want the ignition delay to be very short in a diesel engine. So we want it to have what's called a high cetane number, so it's very easy to ignite. That tends to make the engine run better. On the other hand, gasoline engines, spark ignition engines, running Otto cycles, use a spark. And if you're using a spark, you don't want it to ignite at some different time. You only want it to ignite when you put the spark in. So if it ignites it at the wrong time, for example, before the spark ignites, then you have a problem. And that's called knock when it happens in an Otto engine. And that's really undesirable. And this can be really bad. So this is an example of a hole that was formed inside the piston head by knock on a gasoline engine. So you don't want this to happen to your car. It's going to cost you a lot of money to get it fixed. So you don't really want bad knock in your car. Even mild knock. Have you guys ever heard that? If you try to like accelerate a weak car up a big hill, you can hear it like rattling in the front, and that's typically from kind of gentle knock in the cylinders. It's not every cycle, but some of the cycles are knocking. And it's annoying. It makes a noise. It bothers you. If you keep doing that for a long time, you're risking that you're going to do something bad to your engine. So this is quite important in the gasoline engines. It turns out that this constrains the compression ratio. If you compress the piston too much, you'll get knocking all the time. So they have to back off and only compress a certain amount in the gasoline engines to avoid the knock. But you get better efficiency with higher compression ratios. So you're sacrificing efficiency of the process of going from heat to work in order to avoid the knocking problem that might break your engine. And so if you could get the fuel not to knock, then that would be better, and you could make higher efficiency engines with higher compression ratios. In the diesel engines, the ignition delay is about 50% due to the chemistry, and that leads to the cetane spec. And then the other 50% is due to stuff about the droplets that we talked about the other day and the fuel injection and how fast you get things to evaporate, because you can't burn until it evaporates. And some other engine concepts are really sensitive to the fuel ignition. And so there's like you might have heard of RCCI or HCCI. You guys ever hear these things? Yeah, these are like modern engine concepts that have advantages over diesel or gasoline, but haven't really caught on, partly because of difficulty to control the ignition delays correctly. They're very important. If you're going to change to an alternative fuel, you have to make sure that it can operate in the engines we have. And so you have to worry a lot about this ignition delay thing. And then there's another problem in jet engines. A particularly bad thing can happen is occasionally a combustor will blow out. So you have no flame in one of your jet engines. And then you really want it to relight, like before you hit the ground. So they have a spark and a bunch of stuff in there to try to make it relight. Exactly what's happening there, not so clear. You'd typically be up at some high altitude. It's really cold. Who knows, is the fuel still evaporating? What's going on? The pressure's low. It's a little bit weird. They have the sparking like crazy. You're trying to make it light. But there's a correlation that things that have higher CT numbers that ignite easier do better in the relighting tests. So people think it's somehow related, but exactly how that works, I do not know. So because this is really important, the low T ignition has been studied a lot, and there's a bunch of review papers and books about it, all mentioned here, these different papers. Actually, this is a whole book, Computational Chemical Kinetics. And we have very detailed quantitative understanding of some of the fuels. But there's a lot of things about this are kind of not quite right. And so here's like just my perspective on the low T ignition problem. So in general, ignition delays are very well behaved if the initial temperature is low or high, but behaves really weird in the intermediate region that's called the NTC region, the negative temperature coefficient region. What's happening is that at high temperatures over here, this is Arrhenius inverse temperature scale, high temperatures, you get very straight Arrhenius behavior. Everything behaves kind of about the same. It's all kind of normal, no problem. But then as you lower the temperature, suddenly the ignition delays drop, and you get like extra ignition, faster ignition than you might expect. But then as you keep lowering the temperature some more, they get long again, as you might expect. And this is a different Arrhenius slope than the one over here. So that's a phenomenon. And this bend in the curve when it goes down and up is this non-monotonic with temperature. That's called the NTC region. And the slopes of these lines over here in the very low temperature region, they're all similar. And in fact, there's like a simple rule of thumb about how to estimate the effective EA of the ignition delay related to the EAs of some specific reactions. I'll talk a little bit more about that. And then over on this side, it's just a couple reactions are controlling, and we sort of understand it pretty well. But what's happening like in here is kind of a mess. So let's explain. At high temperatures, when you make a radical at high temperatures, it unimolecularly reacts very fast, typically to some of them spit out an H atom after that when they decompose. And they kick out a bunch of alkenes. Remember we mentioned that the fuels pyrolyze, the big radicals break down to small radicals plus alkenes. This happens super fast at high temperature. And then when you make some H atoms, they react with the oxygen that's present to make OH plus O, and this makes more radicals. And this whole thing is super fast because this step is super fast, zip. And then this is fast too because you have a lot of oxygen. So basically, as soon as you form an H, about 1/5 of the molecules in the mixture are O2s. And so you just react to them right away. And then you make the radicals. And this unimolecular reaction of R dot is faster than its reaction with O2. So you don't have to worry about bimolecular reactions at the R dot because it's just going to go away so fast. So that's like a great simplification to understand what's going on. If you're at low temperature, the R dots you make live forever because it's low temperature. They don't have enough energy to do the endothermic extruding alkene reactions. And so they live long enough to react with O2, and almost all of them do react with O2. And at low enough temperature, this guy's reactant just make the RO2 radical, called a peroxyl radical. I'll explain more about what happens next, but that's basically the 100% of the radicals basically do this. At least all the active radicals. Some of the resonantly stabilized radicals don't do it, but most of the radicals do this. In the medium temperature, where things are non-monotonic, it's kind of weird. The R reacts with the O2 just like it does here, but it makes a different product. So this has to do with the chemical activation we mentioned, that you can have the same reaction occurring, but the product can change at a certain temperature. So it changes, instead of making this product, it makes this product plus an alkene. And so then you make lots and lots of HO2, and then that leads to formation of H2O2, and you get some cycles there. In this region, the reason you don't make RO2, one of the reasons is that this equilibrium favors R instead of RO2. So you're kind of above the ceiling temperature for this equilibrium. So at low temperatures, R plus O2 goes to RO2 pretty much irreversibly. But when you get a high enough temperature, this equilibrium stops running. And this reaction stops running because it reaches equilibrium quickly. And so then the Rs can't really do this anymore. So instead, they have a sort of side channel where when these guys combine, they don't have to make RO2, they can make HO2 plus alkene, and that one still runs. Right, yeah. Yeah, it depends on the fuel molecules, the fuel composition, the temperature, actually a lot of other stuff too. Pretty complicated. Yeah. Yeah, sorry. The question was, does the NTC region depend on the pressure? All right? Yeah. And the oxygen concentration, yes. Yeah, so, and the answer is yes. So the NTC region depends on the pressure. It depends on the oxygen concentration, partly because this equilibrium depends on the oxygen concentration. It depends on the temperature, because this equilibrium definitely depends on the temperature pretty strongly. And so, and it depends on the fuel composition too, maybe partly because the way this reaction goes to break down depends on sort of what alkene you make, and that each one will be different for different fuels. So you get quite a complexity of what can happen. And then you have, in this medium temperature region, the H atoms mostly react with O2 to make HO2 by this pressure-dependent process we talked about before. And that means that the H atoms are not available to do this other reaction so much. Or this reaction is very favored compared to this one at this temperature range. If you go up higher in temperature, then this one wins. So it's, and this competition also depends on the pressure. So let's sort of follow what happens in ignition. So suppose we start at low temperature here, like around 650 Kelvin, and we have some fuel, and we're oxidizing it. And what we'll see is that initially, any radicals we make from the fuel react with oxygen. They make RO2. The RO2 isomerizes and ends up making this stuff. I'll show the reactions for that in a second. So you make this intermediate called a keto hydroperoxide as like the main intermediate. Make quite a lot of it. And then this reaction is oxidizing the fuel, so it's releasing some heat. So you're getting some temperature rise. And when you get to some crucial temperature rise, this guy starts to go down, and it's breaking the OO bond to the peroxide. That makes radicals. The radicals attack the fuel, make a lot of other stuff happen. And some of this stuff makes formaldehyde. And you also start to get hydrogen HO2 formation and hydrogen peroxide. So then you have a different stage. So there's like different stages. There's a stage like when this really takes off, called stage 1A. Then there's a time when you reach the peak of the keto hydroperoxide. That's a different time. Then a little bit later, there's a time when this one goes away and the hydrogen peroxide starts to come, and the temperature usually goes up too. That's a different stage, and the chemistry changes. And then suddenly, when you get to a certain point, all of a sudden, kaboom, the temperature zooms all the way up, and all your stuff burns up. And that's the explosion. So this is really the time that you would measure as the ignition time when all of a sudden you have a fire. Yeah. Yeah. Yes, I think all of them have been measured. This one's kind of hard to measure, but I believe Jackie Sung at Connecticut measured it, and somebody else did too. I can't remember. What? I think he did he sampled from rapid compression machine. I think he did it. But anyway, I'll check. But there's some data for this. These ones are definitely measured a lot of times. People see them. He probably just gets like total peroxide or something like that. Yeah. And then once you get above the high temperature, then you know what's going on. So up here, what happened was that the temperature started going up, and once you get high enough, then you get into the high temperature regime, and boom, it just goes. Because the ignition delays at high temperature are really short. If you remember back from before, this is a logarithmic plot, so the time scales down here are really, really short compared to the time scales here. This is like more than a factor of 100 change in time scales. So once you get to this kind of chemistry, by comparison, if you're on the same scale, same time scale, this looks instantaneous. It's not really instantaneous, but it's really, really fast by comparison to this really slow stuff that happened before you get there. And the consequence is that this stuff often controls the ignition time, is all this low temperature stuff, because it's so slow. All right, so you get a lot of, we have the rough idea of what's happening. At the high temperature, because all the big radicals just fall apart, it's actually a huge simplification. So you can even do very complicated fuels like real jet fuels. And the Stanford high chem team has done it, where they empirically took a bunch of jet fuels and measured how they decomposed, and then figured out the ignition delays of the decomposed stuff, and they really can understand exactly what's happening. And so at the high temperature, the issue is not really the ignition, but stuff like soot formation and the coupling with the flows and stuff. The ignition is not really a problem. The key concept to understand ignition is about chemical amplification. So it's primarily how fast can the number of radicals grow. So if you put a little tiny bit of radicals in, do you get 1 million more radicals out, or do you put a little radicals in and they just react away and they're gone? It's like the two cases where you have ignition or you have misfire. Nothing happened. In general, you can kind of model this as the radicals are growing or shrinking exponentially. And the whole thing has to do with the eigenvalue here. Is this a positive number or a negative number? And if it's positive, what's the time scale? How big is this lambda? Because that's going to set the time scale of how fast the radicals grow. And so it's very helpful to analyze the Jacobian of the chemistry, figure out the eigenvalues, and then often you'll have like one positive eigenvalue, and that will be the one that's controlling to make the explosion happen. And I think people will do this for other kinds of explosions. You guys familiar with this at all? So there's this general idea that in chemistry, most of the eigenvalues of the chemistry of the Jacobian are almost all negative. Everything wants to relax towards equilibrium normally. But if you get a case where there's an eigenvalue that's positive, that means the thing wants to explode. And so that will dominate very quickly. No matter how you start, the one that's the positive eigenvalue is growing, and all the other ones are exponentially going away. And so the mode that corresponds to the positive eigenvalue becomes dominant very quickly. And that's what you really have to look for to understand why it would ignite. So at medium temperature, the really important one is the HO2, H2O2 amplifier. So I'll try to explain how that works. So if we have H2O2, there's kind of two important reactions it can do. It can react with itself to make hydrogen peroxide, or these guys, each of them can separately react with a fuel molecule. And when an HO2 grabs an H from a fuel molecule, you get an H2O2 also. And when this happens, you also get an R dot. So if they go this way, The two H2Os will make two radicals and a mole of H2, 2 moles of H2O2. If they go this way, they'll just make H2O2. If you go around the blue cycle, it's neutral. It doesn't make more radicals. You have two radicals in, you get two radicals out, they make two more radicals, they make two more radicals, these guys make two radicals. So this is like a neutral cycle that's running all the time, but it doesn't affect how many radicals you have. You sort of get like in a pseudo-steady state of all these guys existing together. But every time the reaction goes this way, where the HO2 reacts with fuel, then you get more H2O2, 2 moles of H2O2, and you get and you short circuit this cycle. And the more H2O2 you get, the faster you form the radicals, and so you get an amplification. Or sort of like all these guys grow in consort with the concentration, the steady state concentration of H2O2. So this goes up, then all the radical concentrations also go up. And you can write down what the eigenvalue is analytically here, and it turns out that it's a couple of rate coefficients times concentration of fuel, because this is the key, is the HO2 has to react with the fuel. That's the slow step. And that's slow because it's endothermic. HO2 is a very weak radical. It doesn't really want to abstract an H. So it's about 12 kcals per mole endothermic for that reaction to happen. So it's kind of slow. So mostly it wants to just recombine. But if you're warm enough, some of them will go this way. And that leads to the amplification. And then as it goes, each time you do that, you're oxidizing a fuel molecule, so you get more heat. So then the next time around, it's faster because it's hotter. And it gets faster and faster and faster and explodes. So we understand this kind of moderately well. It's definitely sensitive to all these things. We think we know most or all the reactions. HO2 reacts a lot of ways, and some of the rate coefficients are not known perfectly. So for example, HO2 can react with the radicals also. And you get two different possible products, and we don't really know the branching ratio to these two different products. This one's happening on a triplet surface, because O2 is a triplet. This one's on the singlet surface. You're most sensitive to HO2 plus RH, but this is not the main reaction consuming the fuel. The OH reacting with the fuel is actually the main consumer of fuel. If you go back here, OH is reacting with the fuel to make Rs, and that's running all the time and burning a lot of fuel, but it doesn't increase the number of radicals. This is just a linear process of just gradually converting the fuel. This one is an amplification process that makes more radicals, which makes more OHs, means it's going to burn the fuel faster when that happens. All right. If you go back to low temperature, at low temperature, the Rs all react with O2s to make RO2s. And then these guys mostly isomerize to this thing called a hydroperoxy alkyl radical, where the O2 grabs an H off the chain of the radical, of the R. And then this thing can add O2, and you end up with this keto hydroperoxide. And this keto hydroperoxide this one still has a radical, OO dot. It can abstract another internal H and make this diperoxide thingy, and that falls apart to keto hydroperoxide. And this mostly loses the OH and makes two radicals. And so you get chain branching because you got two radicals here and one here. So you get three radicals out for one radical in. You put R dot in, you get 1, 2 OHs, and also this funny radical. And so this is an amplification, but it's a little complicated. You can see, I have to use like special notation to help you see it. And each fuel has a different R structure, which also a different Q structure. Therefore, all these rate constants and equilibria are all different. And there's a whole bunch of competing side reactions written on the right here, which can affect the overall flux of how much of it goes to make radicals compared to other stuff. And a particularly important one is this cyclic peroxide thing, that this intermediate, instead of falling apart, can go instead to make cyclic stuff. And this one also. This one can go to make cyclic stuff. And you can measure these cycles, and sometimes these can be quite high. Actually, I think Jackie Chen also measured the cyclics. And for certain fuels at certain conditions, you might get like half the mass might go to these cycles instead of going the way you want it to go. This is how the reaction looks. the peroxyl radical RO2, this is RO2, it extracts, say, this H right here to make the radical there. Then that adds O2, so now you have an O2 there, and that's a peroxyl. And that guy does the same thing again, except this time it grabs the H that was right here. So this O2 reaches back and grabs that H off. And when it does that, it makes a radical here, but it immediately falls apart and makes a carbonyl and kicks out the OH. So we make an OH and this carbonyl oxyl radical. And, take that back. It goes here, makes the keto hydroperoxide plus this OH. Then this guy breaks the O bond and makes the oxyl radical plus the second OH. So the addition of the first oxygen to make this guy and then the second oxygen is really important. And so you have to have a radical that's big enough that it has two sites in the right position so it can add the two oxygens. You can measure this by measuring the total heat release, so the pressure. So for example, if you just use pure isooctane in an HCCI engine, all you see is ignition at some high temperature. But if you put a lower octane mixture, this is octane 80, you see a bunch of heat release happening very early, but then nothing happens, and then you get kaboom later. And this first part was the low temperature proxy chemistry happening, but it didn't reach a condition that led to ignition yet. So it just started to run, released some heat, made some peroxides, and then later when the temperature got a little bit higher, then suddenly they all exploded. And this is quite important. So this is really, the cetane or octane is controlled by this kind of stuff. And you get this super fast growth initially of the radicals from those very low temperature cycle with the keto hydroperoxides. And then you get, the temperature gets warmer and it turns off that channel. And it turns out this H2O2 cycle is kind of slower. So you get like a fast thing and then a slow thing and then a really fast thing at the end. And so that's sort of what happened here, is that in this region, the chemistry turned off because it got too hot. So the R plus O2 reaction got equilibrated and it couldn't run anymore. And then later, a whole new channel opens up when the H2O2 decomposes. People have done a lot of experiments to try to understand this empirically. And there's a lot of numbers like the blending octane number, and you can look up the IQT-derived cetane number. And there's a whole bunch of numbers like this, and the industry uses them to try to qualify fuels and figure out which would work. There's a lot of problems to try to understand this. And this is like kind of a mess, actually. So we're trying to, people would really like to understand this for all kinds of fuels. And if you have a new fuel, you'd like to be able to understand what its chemistry is going to be at all these conditions. But the reactions are complicated. If you have a lot of compounds, they all kind of do slightly different things. And so it's a little confusing. Sometimes you see what's called two-stage ignition. So let's see if I can explain this. That when you start to, let's see, you're at very low temperature, you have a long ignition delay. When you lower the temperature, you see something happen where the temperature rises, and then there's another delay, and then it rises a lot. It goes up in stages. And so you see the first step is at this time, and the second step is at this time. And this is for dimethyl ether. If you do the same thing with methyl cyclohexane, you get the same kind of behavior, just at a different temperature and wildly different ignition delay times. Many fuels do this if you start it from the low temperature side, where you can see that something is happening, but it's not really ignited all the way yet. And then if you wait a little bit longer, it might ignite all the way. And you can compute it. So this is, we did the computation of what's happening in propane, and you can see how the OH radical is like zooming up 5 orders of magnitude in less than a second. And then it's rising still, but very slowly. And then it actually it dips. The OH goes down, and then it kind of hangs out for a while, and all of a sudden, kaboom, it goes up. And that's the explosion. And so you have to have a pretty good simulation to get this correctly. And the experimentals sometimes can see this if they do careful experiments. And the experimentals often would see this little dink of the temperature rising. before the ignition. So they see this first stage ignition where something happened, and then the big ignition later. So good news about this is not as bad as you might think, because there's these three clear types of chemistry happening, and there's only a few reactive intermediates that matter. So you don't have to worry about everything about the fuel, just about these particular intermediates. And you can see the stages. And a good way to understand the low temperature amplifier, say, well, the OH reacts with fuel, makes the R radical adds OO. This guy equilibrates the QOH, this guy adds O2, and then this one breaks. It does another isomerization that breaks it, and kicks out an OH, and then kicks out the second OH. And if you understand these, all these steps, 1, 2, 3, 4, 5, 6, actually this one too, 7 steps, that's all you need to understand it. So you don't need 1,000 reactions, you need the seven reactions, but then times the number of fuels you have, because each fuel will have different numbers for each of these reactions. And if you look at it as a cycle, the key question is whether you have positive gain or not. So do you get more OHs out than you put in? If you do, then you're having a chemical amplifier. And just like in a microphone amplifier, if you hold it next to a loudspeaker, it screeches because the noise suddenly goes up. It's the same thing happening here, is that if you're in a situation where you'll get more OHs out than you started with, then immediately the OHs will zoom up. And we can write down what the eigenvalue looks like. And the key question is, like, are these the fractions of the OH that go each this way, this way, this way, are those, if you multiply those numbers together, if they're all equal to 1, that means it goes all the way around, then you can just write down analytically that the eigenvalue would be the ratio of the product of these two rate coefficients. Actually, yeah, and that's all you need to know. But sometimes you lose some of the radicals because there's a side reaction to something else. And so then these alpha, beta, gammas might be less than 1. If you consider all those side reactions, it gets kind of complicated. But you don't have to worry about that too much. And you can see that the OH and the HO2 initially grow together exponentially, but then they diverge in the middle region. But then they track each other for a while, and then they track each other at the end too, because everything grows exponentially together in these cycles. And the Ni is when the HO2 plus HO2, when the HO2 gets so high that the second order reaction of HO2 becomes competitive with the HO2 plus fuel. That's when you see this like dip there. Yeah, and so if there's an explosive eigenmode, it's the only thing that matters. Oh, I better stop and give you guys a break.